All right, so here it says select the incorrect statement regarding the boiling points of alkanes. Now, let's read them over. Boiling point increases with stronger van der Waals forces. Surface area is the only factor that determines the boiling point of alkane. Boiling point of a straight chain alkane is greater than the branched chain, and the boiling point of cycloalkanes is always higher than the linear alkanes. So which one do you think is the incorrect statement?
B.
Yes. So do you mind explaining it, or would you like for me to explain it?
Because the type of bonds, like a hydrogen bond or a van der Waals force, also determines the boiling point.
True.
And the number of carbons.
Exactly. So here, for example, A. Why is A correct? Because the more you increase the number of van der Waals forces, the stronger the bond is. So stronger the bond. Anyway, so the more you increase the number, the stronger the bond of the force is. And the same thing when you increase the surface area. So here, for example, boiling point of the chain alkanes. For example, we have a chain. Yeah, so we have a chain alkane. And now it's attached to another chain alkane. So now you have greater surface area than one that's branched, than with another one that is branched, for example. So the surface area here is less than a straight line, a linear alkane. And lastly, the boiling point of cycloalkanes is always higher than that of linear. That is correct. So if we take cyclopropane, for example, and a regular propane, you would find that cyclopropane is like negative 32 degrees Celsius, and propane is about negative 40 degrees Celsius. All right, moving on. An alkane with 6 carbon atoms, how many hydrogen atoms? Do you guys remember the formula? So what's the formula? Could someone tell me?
CnH2n plus 2.
So Cn H2n
plus 2.
Plus 2.
Yes.
Yes. So now if we replace the n with 6, what will be the answer?
14.
Exactly. So those type of questions would usually come in the midterm. Now moving on, the bond angle of a normal tetrahedral, which is sp3 hybridized and has the angle of 109.5 degrees. What is the bond angle of a cyclobutane? So cyclobutane, usually drawn like this, like a diamond. What are the angles on it?
90.
Yes, so it is 90. So the correct answer is 90. Oh, sorry, that's yes, 90. And moving on. So now you guys are getting it, right?
Yes.
So after chapter 2, everything becomes a bit harder. So chapter 2 is like the easy chapters, it and chapter 1. Anyway, cycloalkanes with blank or more carbons in the ring are non-planar. So we took how many? We took let me change it to pen.
4.
All right, exactly. So we took cyclopropane, we took cyclobutane, we took cyclopentane in this chapter, and cyclohexane. So out of those, from where does it start to take a shape that's non-planar, meaning that it's not in one line?
Cyclobutane.
Cyclobutane. If I drew a line from here onwards, they are non-planar, right? So this one takes an envelope. This one has like a puckered shape, and this one has like the chair or boat conformation. So here we would say 4 and above. You guys understood till now?
Yeah, it's all clear.
All right, that's good. Consider this chair conformation. All right, so we look at this. Wait, let me actually put this down to keep it in another slot. Yes, in another page. So consider this chair conformation. Which of the following is correct? The methyl and bromine are cis, and the chlorine and bromine are cis, or the methyl and bromine are trans and the chlorine and bromine are cis, or the methyl and bromine are trans and the methyl and bromine are cis, or the methyl and the chlorine are trans and the methyl and bromine are trans, or the methyl and chlorine are trans and the bromine and chlorine are cis. Take your time, guys. Analyze it.
A.
So
they're
A,
all
right?
cis.
And
Yeah.
why do you think that is the reason?
They're all pointing upwards.
Exactly. So the ones I draw in red here, for example, here, and if we had one here, it would be like this, here, here, and if it was there like this, those in red are what we call up. No matter, even if it was equatorial, or axial, it doesn't matter. So for example, if it's equatorial and another is axial, but they're both upwards, that makes it cis. It doesn't mean that, oh, both are axial خلاص, those are cis. مو شرط. All right? Clear to everyone? All right. Moving on. So the compounds represented by the structures below are what? So this compound and this compound, what are they?
Cis trans isomers.
All right, cis trans. And why is that?
Because at first the methyl groups were trans and now they're cis.
Yes. You remember what I said about equatorial and axial? It doesn't mean that one's equatorial, one's axial, خلاص, then they are cis. For example, those are facing opposite sides. Yes, you are correct. This one's the trans and this one's the cis. Because this one's pointing upwards and upwards, this one's upwards and downwards. So this is a cis and trans isomer. Now moving on, the compounds represented by the structures below are, so here we have another chair conformation. What are those isomers that we're presenting here? What type? Take your time. So we can see here, for example, the Cl is axial, and here it's equatorial. So here we have a flipping incidence, where we flip it from equatorial to axial, and vice versa. Do you guys have any clue?
I know it was called the ring flip, but I don't remember which isomer it is.
No worries. I'll explain. So here, when we have a ring flip, this is a conformer. It's conformer because it's the same molecule, however, we just flipped it, making the axial equatorial and the equatorial axial. So those are conformers.
Okay, thank you.
Understood?
Yeah.
Good. All right, how about here? We have a sawhorse configuration. This one's pretty easy. Make sure to read them carefully. Maybe they change like this with a CH3, then it becomes a different molecule. But in this example, it's the same molecule.
Yeah, it is C, cis trans.
Cis and trans.
Are you guys sure it's cis and trans? Because we just have one what's it called? Bond, and they are rotating on this one bond. So we see that the BR flipped downwards, and here the BR is upwards. And it's just on one bond. What do we call that?
Structural isomers.
Guess again, because we here we didn't change the structure, like the
D.
D,
Constitutional.
E, or D. So let's do the elimination technique. The structural isomers and constitutional are the same thing.
Confirmers.
Yes, they're confirmers. And why is that? Because here we have one. Sorry?
Rotation.
Yes, we have rotation. We're rotating, for example, this Br goes downwards, and we didn't change the molecular structure or anything. It's just the spatial arrangement. And that's what conformers are known for, changing the spatial arrangement. So it was up, then we rotated it on one single bond. Let me draw it in a different color. So, for example, here as in purple, those are just single bonds. So we know that single bonds, you could just rotate them, rotate them, rotate them, and that those are known as conformers. Understood, guys?
When it would be like this picture, when it would be cis and trans.
When would it be cis and trans? All right, that's a good question. Basically, let's say we have a C, and then a double bond C, and then we have Br, and then we have H here, and then we have Br, and then we have H here. This would be cis, and this one would be cis, and if we change the Br and put it down there, it would be trans. And why is that? Because we have double bonds. But here it's just one single bond, so there's nothing known as cis and trans here. It's just conformers, because in a single bond, you could rotate, and that's it. Understood?
Yes. Okay. Thank you.
No worries. And the rest, you guys understood this part?
So on Sohars, we just have conformers. We can't have like any of the options. It's just
Usually,
conformer.
yes. Usually it's just conformer, but sometimes what they like to do in midterms and those big exams like finals is, let's say you have a sawhorse projection, but instead of the BR being, let me use a different color. Let's use black. Instead of the BR being on this molecule, we would have it here, and here would be a H. So that would make it a structural isomer, because now we differ in molecule. We have different molecule. But if you see that in this side, you have the same amount of, let's say, 1Br, 2 H's, 1Br, 2 H's, and here 1Br, 2 H's, and also here 1Br, 2 H's. That means we didn't change the molecule itself. Then yes, it's a conformer.
Okay, thanks.
No worries. Understood this part?
Yes.
Yeah, all clear.
Yes.
All right. We move on. I realized that when I was studying for the midterm that I forgot to revise over the initiation, propagation, and termination steps, and they brought questions about it. So for example, here in the chlorination of methane, so we have a methane, like C, H4, and then we add Cl2, presence of heat or light. So what in the following process of propagation, what would you have? What would form? So you have to look over into this picture right here. So let's see. They asked for propagation. Now in propagation, we could see that we formed an alkyl radical. Then we could see that another radical is formed, which is a Cl radical. So during propagation, you would most likely see two types of radical: alkyl group radical and the halogenation or halogen radical. So let's see in this question. In the chlorination of methane, the propagation steps involve forming H radicals or methyl radicals or chlorine radicals, or all three of them, or just methyl and chlorine. What do you guys think?
Methyl and
Chlorine.
chlorine.
So E, right?
Yes. Yes.
Good job, guys. Yes. So just take a look at it before you enter the midterm, because they might ask, maybe even here, like in initiation, what occurs. You have a product that has two halogen radicals. For example, termination, what happens? Most of the radicals are terminated. Hence, that's why we call it the termination step. Understood, guys?
Yes.
Yes.
Good. All right. So here are other questions. They sometimes ask the reactions in a form of worded questions. How many mono products can be obtained from the bromination of cyclopentane? So let's draw cyclopentane. Yeah, sorry guys. Could you hear me now?
Yes.
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 All right, and you could see the screen, right?
Yeah.
All right. So here, how many monobromo products can be obtained from the bromination of cyclopentane? So we have a cyclopentane plus Br2 with the presence of heat and light. Yeah. How many products would we have? Since we just said monobromo, that means only one bromine attached to the cyclopentane. How much do you think we would have? If I put one here.
One?
One.
Yes. Because and why is that? Why do you think it's just one?
Because
Because
it's
it's
the
the
same
same.
place, same name everywhere.
Exactly. So let me use a different color. For example, if I put it here, or 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 it'll be the same exact molecule. Nothing changed. You understood this part, guys?
Yes.
Yes, thank you.
How about if it was dibromo?
Dibromo would be a different thing. Now, let's say we had both bromine molecules onto the pen. Let me use two different colors. Okay, let's start with blue. So if I put it here, the first one attaches to here, and the second one attaches here. Now we have one product. This is the first product, correct?
Yes.
Now, if I attached it to here, is this the second product? Like instead
Yes.
of having it here, having it here.
It's the same thing.
It's the
Same.
same thing, exactly. But what if I have it here, like this and this?
No, they are different.
Now we have two products, which is this and this, and this and this. And if I attach it here, would this be a different product or the same?
Same.
Same. For now, two products. But then people miss this when they're doing the exam. You could have two bromine molecules on the same carbon. So by this, you have three products. You guys understood?
Oh, so we have three.
Yes.
Not-
So one here. Let me just remove all this. All right. So you have one here, and one here. Let me change the color. And here. And then you have another one sticking with the bromine that's already here. So three products. Understood?
Yes.
All right. Moving on, we have the last question, because I know you guys need to go study. The number of possible monobromination products, including cis and trans isomers of methyl cyclopentane. So this one, it will take time during your midterm. And I suggest for you to take all the time you need to solve this one, because it's an easy question, but a lengthy. So let's say we have a cyclopentane methyl. So we need a methyl group. Let's say, for example, here. Plus, we want a monobromo product. So, for example, like this. And then now we're looking for the product or the possible outcomes. So let me draw the pentane, and then using a different color. All right. So try to do it yourself and tell me how much you come up with. So attach it in every place possible. And you have to include the cis and trans. Don't forget. Usually they'll
6.
mention. Yes, 6. So 6. And why is that? Could you point out the places for me?
First, we could do it with the methyl
Yes.
in the
So
same carbon.
instead of this 3 here, we could have 2, and then Br. Yes. And then what's the other one?
Then next to it,
Yes. The one next to it. Correct. And then what's another one?
we go to the next one.
The next one. All right. And the last one?
And finally, the one after it. But just multiply each one by 2 because cis and trans.
Exactly. So basically, what our friend was saying, is we could add one to the methyl group, and many people miss this one. You could add one here. You could add one to the same carbon that it was attached to. And then when you start adding to ones on different carbons, you start having the cis and trans. So here we could have a cis conformation and trans. For this one's ×2. And here it's the same thing, cis and trans. So this one's also ×2. So let's count them together. We have 1 here, 2 here, then 3 and 4, and 5 and 6. So you guys understood? You guys understood, or would you like to go over it
What
again?
was the first?
Sorry, the first one?
Yeah.
Yeah, so you know how we said it's a methyl cyclopentane, meaning that it has a methyl group above, like for example, right here. So this is the methyl group, correct?
Yeah.
So it contains a carbon. This carbon could also go bromination. So it can become C2Br. And then it attaches to the cyclopentane.
Oh yeah, understood. Thank you.
You understood it? Good. Any other questions, guys?
Just can you scroll up, please?
Yes. Which question exactly would you like?
It was about the what was that? Yeah. Here, yeah.
Yes. Okay.
Down. This one and the next one, I think. Yeah, this one.
Yes. You want me to re-explain it?
Yes.
All right. So here, for example, let me just erase those. Erase. Now we chose the answer as A because A says the methyl. Let me choose this. All right. The methyl and the bromine are cis, meaning they're on the same side. So as the bromo and chloro or chlorine molecule are also cis. And why is that? Because when we have a chair conformation, those sides that I'm highlighting now in blue, those, along with those, are what we consider something called up. They're facing up.
Axial, yeah? These are axial.
No, it's not axial.
Uh,
This may confuse you. Nor equatorial. It's something other than axial and equatorial. They're just cis and trans. What do I mean by facing? Yeah, what do I mean by facing upwards? Meaning they are on one plane. Whether they are axial or equatorial, it doesn't matter. They're just facing the same side, which is up.
So whenever they face in the same side, they are cis.
Exactly. And then you have another one, which now I'm highlighting in purple. Those are considered down. Those are down. Sorry. Yeah, those are down. So those will also be on the same side. The ones in purple are on the same side and they're facing downwards, and the ones in blue are the same side and they're facing upwards. And it doesn't matter if they're equatorial or axial. It's just how they face in real life.
Okay, thank you.
No worries. Now, this question you were asking about?
Yeah, and this one.
Yeah, here the same thing. So we said that it doesn't matter if they're both axial. It doesn't mean that they will always be what's it called? They will always be cis. If they are axial but facing opposite sides, as I told you, down, and this one, let me do it in blue, and this one is facing upwards, this makes it a trans.
Yeah.
But
So one is now one is down and one is up. It would be trans.
yes,
And if both were up, like it would be cis.
yeah, and sometimes if both they're down, for example, like this, both are down, then yes, it's also cis. So they have to be facing the same side.
Mm-hmm.
But
Understood?
Yeah, I got it. Thank you.
But for the question here, like the C and the second one, the CH3 and the H, they replaced the places together from the comparing the first one. So it doesn't matter if they replace places, the bonds.
Yeah, it's just now that this one has become like on the other side, so it's now up rather than it being down. It became up, and that's why we called it cis, because now both of them are up.
Okay.
And we didn't flip. It's not a flip, Because if it was a flip, this would have turned into a equatorial axial. But here we changed the molecule position. That's why we call it cis and trans isomers.
Okay, thank you.
Wait, I just want to confirm. So in the one on the left, the CH3, they're both axial, but it's trans because they're facing opposite sides, right?
Yes, both of them are
Okay.
axial, but they're trans because they're facing opposite sides.
Thank you.
No worries. Any other questions? If not, we could. I'll send this one on the group. No worries, and we could go to Malak. She'll be explaining. Malak. She'll be explaining the chapter 1. Yeah, Malak, your turn.